Mars. The greatest secret is buried beneath the red dust. Red, silent, dry. Or is it? For decades, we've looked at Mars and asked the same question. Is there water up there? Not frozen water, we've found that. Not ancient riverbeds, we've mapped those. But actual, flowing, liquid water today. Now, in 2018, scientists made a stunning announcement. Radar data from the European Mars Express orbiter had detected something strange beneath the ice of the Martian South Pole. A bright reflection, flat, strong, persistent. Too strong to be rock, too reflective to be dry. It looked like a lake, a subsurface pool of liquid water, possibly dozens of kilometers wide, hidden under layers of ice and dust. Liquid, despite temperatures far below freezing. The idea was bold, because if there is liquid water on Mars right now, then everything we thought we knew about the planet might be wrong. It could mean Mars has internal heat. It could mean there are underground ecosystems. It could even mean Mars was never fully dead. But as the headlines cooled, the controversy began. Some scientists said the signal could be caused by salts. Others pointed to dry dust, unusual ice layering, or even radar artifacts. The same data, two wildly different interpretations. So what's the truth? In this video, we'll trace the search for water on Mars. From ancient lakebeds to buried ice sheets. From rover clues to orbiting mysteries. So yeah, like and subscribe for Start This Journey. We'll explore every claim, every debate, and what the next missions might finally prove. Because if we've truly found water on Mars, the implications stretch far beyond one planet. They might change everything. Before the talk of lakes and oceans, Mars had a very different image. Cold, dead, empty. For most of the 20th century, Mars was known as the Red Planet, and it earned the name. From Earth, early telescopes showed a world coated in rust-colored dust, with no sign of clouds, rivers, or oceans. In the late 1800s, astronomers thought they saw canals on Mars, straight lines that crisscrossed the surface. Some believed they were artificial, proof of a dying alien civilization trying to irrigate its planet. It sparked books, speculation, and the idea of Martians. But as telescope optics improved, the canals disappeared. They were illusions, tricks of the eye, and atmosphere. The fantasy faded into silence. Then came the age of machines. In the 1960s and 70s, NASA's Mariner missions sent back the first close-up images of Mars. No canals, no oceans, no signs of life, just endless rock, sand, and craters. The surface looked more like the moon than any place on Earth. In 1976, the Viking landers touched down. They ran experiments, took soil samples. What they found confirmed the bleakest expectations. The Martian surface was frozen, lifeless, and bone-dry. Temperatures plunged far below freezing. The atmosphere was barely there, about 1% the pressure of Earth's, and made almost entirely of carbon dioxide. No rivers, no rain, no visible water anywhere. Mars, it seemed, had once been wet, maybe billions of years ago. But whatever water it had was long gone. Either it escaped into space, or it froze deep underground beyond our reach. For decades, that was the narrative. Mars was a dead desert. Interesting, sure, but hopelessly dry. And yet, there were questions no one could quite answer. Carved valleys, smooth plains, landforms that looked eerily like dry riverbeds, gullies, deltas, and erosion patterns that whispered of flow. And the polar ice caps? They seemed to grow and shrink with the seasons, like they were breathing. Mars looked dry, but just beneath the dust, something was waiting. The clues were always there. We just hadn't learned how to read them. If Mars is a desert today, it wasn't always. From orbit, NASA's spacecraft began spotting strange features etched into the Martian surface. Winding channels, branching valleys, fan-shaped deposits. They weren't random. They looked familiar, too familiar. They looked like riverbeds. These were the first signs that something once flowed across the Martian landscape. In the early 2000s, Images from a Mars global surveyor revealed entire networks of dry channels, many stretching for hundreds of kilometers. Some began in crater walls, winding outward like rivers do on Earth. Others pooled into basins, creating what appeared to be ancient lakes. In 2004, the Opportunity rover landed in Meridiani Planum, and it found more than just rocks. It found layers of sediment, ripples and stone, and small, round formations known as blueberries, tiny iron-rich spheres shaped by water. These weren't just dry landscapes. They were shaped by water over time. Carved, eroded, settled. The evidence piled up. Craters filled with delta fans, like the ones rivers build when they slow and spread. Canyons with winding paths, just like water makes when it cuts through rock. Mineral stains along cliff walls that suggested seeps or springs. Even more astonishing were massive outflow channels, areas where water may have once burst forth in catastrophic floods, carving deep scars into the land in a matter of days. One of the most striking finds was Jezero Crater, a massive impact basin with clear signs of an ancient river flowing in, and a fan-shaped delta still visible from orbit. That's where Perseverance landed in 2021, not randomly, but because of the signs of ancient water. Scientists believe Jezero once held a standing lake, possibly for thousands of years. A stable body of water where sediments collected and maybe life evolved. But it goes deeper than geography. When water flows, it leaves behind more than just shape. It leaves behind chemistry. Rovers have detected clay minerals, formed only in the presence of water. They've found sulfate salts, hydrated silica, and other compounds that require wet conditions to form. This means water wasn't just a one-time event. It was sustained. Mars had rain, rivers, lakes, maybe even seas. Some scientists now believe that early Mars, over 3 billion years ago, may have looked more like Earth than the Mars we see today, with blue skies, running water, and a magnetic field strong enough to hold its atmosphere. But something changed. The planet cooled. The magnetic field faded. The atmosphere thinned, and the water vanished from the surface. Or did it? Maybe it just went underground. Because while the ancient rivers are dry, the next clues suggest water didn't disappear. It just went into hiding. Rocks remember, even when rivers dry up and lakes vanish, the minerals they leave behind keep the memory. And on Mars, those minerals are everywhere. Once scientists spotted the signs of ancient flow, they turned their attention to the surface itself, the chemistry of the rocks. What they found was extraordinary. Using spectrometers aboard orbiters like Mars Reconnaissance Orbiter, MRO, and Mars Express, NASA and ESA began detecting hydrated minerals, minerals that only form in the presence of water. One of the most important discoveries was clay. On Earth, clays form when water interacts with volcanic rock over long periods. Finding them on Mars meant more than just a splash. It meant stable water, the kind that sticks around for thousands, even millions of years. Clays were spotted in ancient crater basins, river deltas, and valley walls, places where water had clearly moved and possibly pooled. In some areas, the orbiters detected phyllosilicates, a group of clay minerals that form in neutral pH water, which is more favorable to life. Not acidic, not alkaline, just balanced. Conditions where microbes might feel right at home. But clays weren't the only clue. NASA rovers found sulfate salts, particularly jarosite, which forms in acidic water, and silica-rich deposits left behind by hydrothermal systems. These hinted at hot springs, geysers, or steam vents, all environments known to host life on Earth. In some cases, layers of these minerals were stacked like pages in a history book, telling scientists when Mars was wet and when it began to dry. One of the most surprising finds came from Gale Crater, where the Curiosity rover landed in 2012. As it climbed Mount Sharp, it passed through rock layers that transitioned from clay-rich to sulfate-rich, showing the gradual loss of water over time. It was like watching a planet's climate change, 1 meter at a time. Even the colors told a story. Blue-green tints in orbital images signaled the presence of certain hydrated minerals. Rusty reds and yellows revealed oxidized iron, possibly from ancient water interacting with volcanic material. But the implications go beyond visuals and chemistry, because these minerals trap organics. They can preserve biosignatures, traces of past life. Just as clay on Earth can preserve ancient pollen, microbes, or carbon chains, so too might Martian clay preserve something unexpected. The deeper the scientists looked, the more Mars revealed its past. Not just a wet planet, but a chemically diverse one, with multiple water environments: fresh, briny, acidic, alkaline, ponds, rivers, lakes, perhaps even underground aquifers. And where there's water and chemistry, there's potential. The minerals on Mars tell us that water wasn't just there, it changed the planet. It altered rocks, shaped landscapes, and may have created habitats for life. But that's only part of the story. Because even today, long after the surface has dried, there are signs that water might still exist. Hidden, frozen, or maybe still liquid. While evidence of ancient water transformed our view of Mars's past, the next surprise was even more direct. Water still exists on Mars, and we can see it. It's just frozen. From orbit, Mars has two distinct polar ice caps, one in the north, one in the south. They change with the seasons, growing in winter and shrinking in summer. At first, scientists believed they were made mostly of carbon dioxide, dry ice. And that's partly true. But under that dry ice lies something far more important: water ice. Massive quantities of it. In fact, if all the water ice locked in the Martian poles were melted, it could cover the entire planet in a global ocean 20 to 30 meters deep. But that's just the beginning. In 2008, the Phoenix lander arrived near Mars's Arctic Circle. It extended its robotic arm, scraped into the reddish soil. And there it was, bright white ice, just centimeters below the surface, staring back at us. It wasn't a theory. It wasn't a radar echo. It was visible, physical proof. Over the following days, that patch of ice vanished, sublimated into vapor, gone with a thin Martian wind, exactly as predicted. But it confirmed something extraordinary. There is water ice just beneath the Martian surface, in many places and closer than we thought. More discoveries followed. Orbital radars mapped massive buried glaciers, some near the poles, others closer to the equator, shielded by a thin blanket of dust. Even mid-latitudes, like the Utopia Planitia region, showed subsurface ice deposits within reach of a future drill. And this changed everything for exploration, because water is the most essential ingredient for astronauts. To drink, to breathe, to make rocket fuel. Without water, Mars is a graveyard. With it, it's a new frontier. But there's one more reason this ice matters. Where there's frozen water, there may once have been liquid water. And where there's liquid water, there might still be life. Yet even with ice proven and mapped, one haunting mystery remained. Was any of it still liquid today? Could Mars be hiding not just memories, but a secret reservoir? The next discovery would rock the scientific world. In 2018, something unexpected happened. A European spacecraft, Mars Express, sent back radar data from beneath the planet's icy south pole. It was part of a long-term study using an instrument called MARCIS, designed to look beneath the surface. And what it found shocked everyone. The radar signals bounced back with unusual intensity. A sharp, bright reflection buried 1.5 kilometers below the ice. It stood out, not like rock or dust or frozen CO2, but like something else, something liquid. The team analyzing the data made a bold claim. They had found a subsurface lake on Mars. A pool of liquid water 20 kilometers wide, buried deep, trapped under layers of ice, hidden for who knows how long. This wasn't theoretical. This was the first direct evidence of a stable, present-day reservoir of liquid water on Mars. The news made headlines around the world. Could this be it? Could we be looking at the first real Martian lake? On Earth, subglacial lakes exist in Antarctica and Greenland. some of them isolated for millions of years, harboring unique ecosystems. If Mars has anything similar, we may not just be looking at water. We may be looking at a habitat. But how could water stay liquid beneath such intense cold? Temperatures at the base of the Martian polar ice sheet can drop to minus 70 degrees Celsius or lower, far below freezing. And yet, the reflection was there. Scientists proposed an explanation: salts. Mars is known to have large amounts of perchlorate salts, which can dramatically lower the freezing point of water. Combined with pressure from the overlying ice, these salts could keep water in a briny, liquid state, like an underground saline pool. Still, not everyone was convinced. Follow-up studies tried to replicate the findings. Some confirmed similar reflections nearby. Others raised doubts. Critics argued that certain types of frozen clays or volcanic rock could also reflect radar in similar ways. Some pointed out inconsistencies in how the signal was processed. Others said the data lacked depth resolution, making it hard to confirm the thickness or nature of the layer. Was it a lake? A sludge? A trick of light? The debate raged on. In 2020 and 2021, further analyses revealed additional bright patches, suggesting multiple lakes or pools might exist. But again, interpretations varied. Each new discovery added weight to the theory, but also raised new questions. What everyone agrees on is this: if the signal truly represents liquid water, it's a game changer. Not because it's the biggest lake, but because it will be the first stable liquid water found on another planet. And that opens up possibilities: microbial life, geothermal activity, even the remnants of a deep Martian biosphere. For now, we don't know for sure, but something is down there, something that reflects radar like water. And whatever it is, it's rewriting everything. Big claims demand even bigger evidence. And the idea of a liquid lake beneath Mars? That was about as big as it gets. Almost immediately after the 2018 discovery, the scientific community split into two camps: the hopeful, who believed we'd finally found present-day water on Mars, and the skeptical, who warned the data might be misleading. Let's break it down. The evidence came from a radar instrument, MARCIS, aboard the Mars Express orbiter. It sent radio waves through Mars's polar ice, reading the echoes that bounced back. The bright reflection from deep below the surface was consistent and intense, a signal that, on Earth, would indicate liquid water. But radar on Mars is tricky. One of the biggest challenges is that radar echoes aren't unique to water. They can also be produced by frozen clays, dense salt deposits, or layered volcanic rock, all of which might exist beneath the Martian poles. And then there's the temperature problem. At those depths, the ice can plunge to minus 70 degrees Celsius or colder. To keep water liquid under those conditions would require incredibly high concentrations of salt, even higher than the saltiest brine lakes on Earth. So high, in fact, that the resulting water might be too toxic for life. A chemical soup, not a welcoming habitat. Other critics focused on methodology. Were the radar settings tuned correctly? Was noise filtered out properly? Was the model accounting for temperature, density, and impurities? Some researchers ran simulations and argued that the bright signal could arise from dry materials layered in specific ways. Others suggested instrumental artifacts, reflections that look like water but aren't. Meanwhile, more bright radar spots appeared, but they weren't always where you'd expect water to be. Some were found in regions too shallow or too cold to realistically contain liquid reservoirs. This raised a hard question. Were these signs of hidden lakes or just optical illusions? Still, defenders of the liquid lake hypothesis pushed back. They pointed to similar radar returns from Earth's subglacial lakes, like Lake Vostok in Antarctica, which remained undetected for decades. They argued that no known dry material could consistently reflect radar this way under such conditions. Some speculated that geothermal heat might exist beneath the ice. Others proposed interactions between salts and pressure that could maintain liquid pockets. A few even hypothesized volcanic activity hidden below the pole. But none of these scenarios has been confirmed. The reality is we're limited by our tools. Radar is powerful, but it can only go so far. It can hint, it can suggest, but it can't drill, sample, or prove. That's why many scientists are calling for new missions. Advanced orbiters, ground-penetrating radar, heat sensors, even a cryobot, a robotic probe that could melt through the ice, descend into the unknown, and give us an answer. Until then, we remain stuck between possibility and uncertainty. The Martian lake could be the greatest find in planetary science. Or it could be a mirage, a brilliant misunderstanding. Only time and better tools will tell. Why does liquid water matter so much? Because on Earth, wherever we find water, we find life. From deep-sea vents to boiling hot springs, from Antarctic subglacial lakes to deep underground rock layers, life finds a way. Even in total darkness, under crushing pressure with no oxygen, if there's water, life adapts. So if Mars has water, even just a tiny, briny, salty pocket, then life might have a chance there too. We're not talking about fish or forests. We're talking about microbes, tiny, resilient organisms, extremophiles, like the ones thriving in the harshest corners of Earth, bacteria that survive in radioactive zones, archaea that metabolize iron or sulfur, microorganisms that live inside rocks, in environments with no light or warmth. Could Mars host something like that? Not now, maybe, but once? The ancient rivers, lakes, and oceans suggest that Mars had millions of years of flowing water. That's enough time, at least on Earth, for life to emerge, evolve, and possibly endure. And if Mars did develop life, even at a microbial level, some of it might have retreated underground, hiding from radiation and freezing temperatures. That's why the search for water is really the search for life. NASA's Perseverance rover is already exploring ancient lake beds in Jezero crater. It's collecting rock and soil samples, potential carriers of biosignatures, chemical fingerprints left by ancient organisms. These samples will be brought back to Earth in the early 2030s, giving scientists the best chance in history to find direct evidence of Martian life. But fossilized microbes aren't the only goal. Some researchers believe that living microbes might still exist, trapped inside the ice or swimming in a buried saltwater lake. Such places would act as time capsules, protecting fragile life from the harsh surface for billions of years. And if we find it, even one living cell, it changes everything. It proves that life is not unique to Earth. It proves that biology is not a fluke, but a cosmic pattern. It will be the most important discovery in the history of science. That's why we keep searching, not just to know Mars, but to understand ourselves. Because if life can exist on 2 planets in one solar system, then it probably exists everywhere. Mars has given us hints, signals, and shadows. Now it's time for answers. And for that, we'll need new missions. NASA, ESA, and other space agencies are already preparing the next wave of explorers. Machines designed not just to observe Mars, but to solve its mysteries once and for all. At the heart of this effort is the Mars Sample Return mission. In the 2020s, the Perseverance rover is collecting rock and soil samples from Jezero crater, a site that once held a lake and likely supported long-term water. By 2033, those samples are expected to be flown back to Earth in one of the most ambitious planetary missions ever attempted. Once here, they'll be examined with tools far more advanced than anything we can send to Mars. We'll search for biosignatures, organic compounds, and the tiniest hints of ancient life, preserved in Martian rock, untouched for billions of years. But that's just one path. NASA and its international partners are also planning missions to explore Mars's icy poles. The proposed Mars Ice Mapper would scan the planet with high-resolution radar, looking for underground water ice, not just to satisfy curiosity, but to support future human survival. Knowing where water is could determine where astronauts land, where they dig, where they build. ESA's ExoMars rover, named Rosalind Franklin, is designed to drill 2 meters beneath the surface. Why that deep? Because radiation destroys organic material near the topsoil. But deeper down, biosignatures might be preserved. After delays, ExoMars could launch in the next few years, and it may offer our best direct search for Martian life. Beyond rovers, scientists are dreaming big. Concepts include robotic cryobots, probes that melt through polar ice and analyze hidden layers directly. Others suggest fleets of lightweight aerial drones, scouting cracks, vents, and seeps from the sky. All of these missions have one goal: proof. Proof that water is still there. Proof that Mars had or has life. Proof that we are not alone in the universe. Mars is no longer fiction. It's real. It's reachable. And soon, it might reveal the truth we've been searching for all along. So yeah, if Mars truly has water, then it was never just a desert. It was a planet with weather, with rivers, with chemistry, and maybe with life. For decades, Mars was the cold, dead world next door. But with every mission, we've uncovered pieces of a different story. A world shaped by water. A world that once ran blue. We've seen the scars of ancient floods. We've tasted salts in the soil. We've found clays and minerals formed in the presence of liquid. And now, maybe, just maybe, we've glimpsed a lake, hidden beneath the ice, waiting silently beneath the surface. It may be real. It may not. But it's a question too big to ignore. Because if we can find water, we might find life. And if we find life, we're not alone anymore. Mars teaches us that planets evolve, that atmospheres fade, that oceans vanish. But it also teaches us that traces remain, that memory is written into rock and ice, that even on a frozen world, there can be stories left to tell. In the coming years, new missions will land, orbit, drill, and return. They will bring us closer to the answer. And if that answer is yes, yes, there's water, yes, there was life, then Mars is not the end of our search. It's the beginning of a new chapter in science, in exploration, in our understanding of what it means to be alive in the universe. So keep watching, keep asking, because the next big discovery might already be waiting beneath the dust.